All right, guys, good evening. I have been chasing cows, and I'm tired a little bit. Over the weekend, tell you a little story, and then you can fuss at me later on the slide evaluation. That's okay. Over the weekend, I have literally looked at 19 years worth of site evaluations. I've taught at Western. This is my 20th year teaching at Western. And so I've had 19 years of site evaluations. That's 38 site evaluations. And I've been through every one of them over the weekend because I'm working on a promotion that I should have done like 3 years ago, and I'm just lazy because you have to go through all that stuff and then write a narrative and prove that you are doing what you're supposed to be doing. So anyway, finally I did this, and it's really funny. My daughter helped me do it. And the reason I say you can write about this later is because there will be some of you who will say, I loved her stories about the cows and the goats. That was so interesting. Then there will be somebody else who said, I hated those stories about the cows and the goats, because that's what we found in the last 19 years. There was the same class. You would have this page of comments. And it would be literally, it would be that. And my daughter, who's 14, who was helping me, she read probably every comment. I didn't read them. I'm like, I don't even want to know. I've read them once. It's like, that's enough. I don't want to know anymore. And she's like, Mama, these people either love you or they hate you. It's like, you can't win. And it's so funny because one person would be like, I love how she explains things and she gets so excited in the same class. She gets too excited. I feel like she's yelling at me. It's like you can't win. Ever. You can't win. So anyway, I will say something that I've always had going on and on over the years, and I will say this has been and I had it even happen, somebody, in the mornings I'm teaching over here in Central Wing, and sometimes the weather or the temperature in the building is really crazy, and so sometimes the door's open. Well, always I'm loud. I know I'm loud. I know that. And so one day after class, I went down the hall to talk to another lady who has an office down there, and she has helpers that work for her. And I made the comment, I said, I'm sorry I left the door open today. It was kind of hot in there, and I was trying to adjust, trying to get the temperature right. And she's like, oh, it's okay. My workers asked me if you were mad, though. And I'm like, I'm not mad. And she's like, oh, I told him you're not mad. You just get really excited and get loud. And that's something that I saw in these evaluations over the years. It's like she's yelling at us. Guys, I'm not yelling. I can yell. Believe me, I can yell. But I'm not yelling at you. I get loud and I get excited, but I'm not yelling. So I hope you know I'm not yelling at you. I've tried over the years to tone it down. I've tried to put a smile on the yell so that you know I'm not really angry. But it is funny. I tell you what, if you haven't ever written a personal narrative, you should. You don't have 20 years probably of your life that you want to write about because you don't remember all 20. But take 10. It's pretty interesting. Every once in a while, I really encourage you to do that. Every once in a while, sit back, take some time to just reflect on the last 5 years of your life or 10 years of a life, and just put it away. You will appreciate it in another 10 or 20 years. If you don't appreciate your kids, your grandkids will appreciate it. But it's kind of interesting. It's an eye-opening experience, and hopefully you can see growth in those 20 years. You may see some things you regret, and you might have to write that down. I shouldn't have done that. Part of mine says that. Should not have done that. But anyway, kind of interesting. So I will tell you this, then I'll leave that story alone. I really debated on how to start my narrative. I mean, I don't know if you all have trouble writing a paper, but starting a paper, it's like once you get started, you can do it, but starting it is like, oh my gosh. Well, I had two scenarios. I mean, this is a professional thing, but I struggle with just keeping it totally boring. I didn't want to make it boring. And so I really struggled with how to start it. And I ended up, when I get ready to write something, I honestly write it in my head for weeks or months before I actually sit down and write it. And I had two different scenarios I had considered using as my opener for this narrative. And I ended up with one of them, of the two. I put the other one within the paper, but I put the one as the beginning. And I started it with my discussion with you all on matter. And I actually put the conversation that we have about me when I ask you what matter is, and you tell me what matter is, and then I ask you if you do matter, and then we go, and that's the beginning of my paper. So you all are part of my paper. All of my students are. So that's the beginning of my paper. But I thought that was a good way to start it. Not like I said, I thought about it. And my title of it was, if I think I can repeat this right. How did I put it? Well, the title of it was Chemistry, the study of matter and the changes it undergoes. That literally was the title. Then underneath it, it says 23 years and counting, ... Oh, the changes this matter has undergone, or something like that. And so that's me. I've taught for over 23 years, and so I've had a lot of changes in 23 years. So anyway, kind of an interesting thing to do. So you should do your own little matter story. So we're talking about matter changing tonight. That's the whole part of what we're talking about. And to be honest with you, this section that we're going to be doing tonight, or actually the section that we're going to be doing for this test material, is really the chemistry that we've been working toward. Where we finally are is chemistry. The last test material was chemistry. But this is, when people think of what is chemistry, this is what they think of: chemical reactions. That's what they think of. And this is finally where we are. We're finally to this point. So we're taking all the knowledge that we gain from formulas, knowing your ions, not knowing your ions. We're taking all of that information and we're putting it together now. Also, if you remember, I really drilled you with dimensional analysis. Not this page, but the next page is dimensional analysis again. But it's dimensional analysis with chemistry. And so finally, you're going to get to see the application in chemistry. Up until this point, I've just been doing dimensional analysis, and it was a lot of just math. Now you're going to be seeing the application of it with chemistry. And so hopefully the dimensional analysis is easy and the chemistry is the new stuff. That's what I'm hoping. A lot of you have done equations in other classes, and so in like an ICP, Introduction to Physical Chemistry Science, or physical, Introduction to Physics and Chemistry, or physical science class you've had. So you probably have done this. So let's get started. It says chemical reactions are converting one substance to another. And in essence, your reactants yield products. I'm going to face the same way you're facing. Reactants will be on the left side of the arrow, and what's going to be on the right? Products will be on the right. So reactants are on the left, products are on the right. And the equation, the chemical equation, is simply the shorthand method of representing a chemical reaction. All you will have to do in this class is balance your equation. That's all you have to do. You just simply have to balance the equation. I will give you an unbalanced equation. You have to balance it. You will not have to write the products from reactants. I will give you the products, okay? So here's how we're going to do that. You have to make sure the number of atoms of each element is the same on both sides of the equation. So you have to make sure that the left side equals the right side by counting atoms. How do we do that? What do we use to do that? What do we use to balance an equation? You may know from another class. What are they called? Coefficients. Give me a picture of a coefficient. Tell me what a coefficient looks like. It's in front of the formula or symbol. Is it a big number or a little number? Okay, so it's a big number in front of the formula or symbol, which is what it says. We're going to use all the coefficients as whole numbers, and you never write the coefficient 1. We do not write the coefficient 1. They should be whole numbers. They should be in their reduced state, meaning, for instance, I'm going to use this down here for an example. If you had 2, 4, 2, 4, what would you end up doing? Reducing. Okay, so they should be in their reduced state. They should always be whole numbers. And very important, the formula subscripts don't change. You do not change the actual formula subscripts. So once your formulas are set, you leave them. All of our work with chemical equations is because of the law of conservation of mass. Now, we've had the law of conservation of energy. What do you think the law of conservation of mass says? I'll start you off. Mass is what? Guys, please put your phones up. I see phones in laps, and I see phones in laps for some students who are doing well and some who aren't. Put them up, okay? So mass is neither created nor destroyed in a chemical reaction. Mass is neither created nor destroyed in a chemical reaction. Another way of saying this is mass of reactants equals mass of products. Mass of reactants equals mass of products. Give you a little scenario of the changes that I have seen in 19 years, good and bad. Obviously, 19 years ago when I first started teaching, I wasn't a very good educator, to be honest with you. I had very high expectations, but my students were different. They didn't have as many interruptions per se. They didn't have a phone that was in their hands in class. They didn't have a computer laptop that was open all the time or a tablet. It was different 19 years ago. It was a lot different. But I also taught mainly agriculture majors. Now, when I tell stories about cows and bush hogs, you don't know what I'm talking about. A lot of you. Some of you do, but a lot of you don't. But what's interesting is I always just loved those ag majors because I was one of those in a sense. I wasn't an ag major, but I'd grown up on a farm, so I had something in common. And even before I bought the farm where I live, I still felt a kindred spirit with those students. But I knew that they had the philosophy of D for diploma. So their whole philosophy of education was, I just got to get through this class. You guys are a different group. You guys want to make a good grade, and it's refreshing to teach you all. However, the difference in an ag major per se, and I say an ag major, I'm not saying one, I'm stereotyping, which isn't good, but give you an idea here. In a comparison to a set of ag majors compared to you all, overall, the ag majors are people that go out and do it with their hands. You all have been in the classroom and you're very much about making good grades, dotting your I's, crossing your T's, and doing the right thing, but a lot of you guys haven't gotten your hands dirty. And so it's a different group, and it's a different approach to teaching. But something that I've also seen over those same years, no matter whether you were an ag major or a nutrition or dental hygiene or nursing major, I don't have the feel that you guys have even had opportunities, a lot of you, in your education settings. You might have done it at home, but in your later education settings, you were more geared toward checking off boxes and following the directions of the teacher than you were, and I'm not saying it was your fault, than you were of just experimenting for the sake of experimentation and playing. And I think a lot of you have lost that curiosity. I think a lot of you are worried that if you tried something kind of weird, people might look at you funny, and so you don't want to try anything. But I've got something super simple. It'll take 3 minutes. I want you to try, okay? and it proves the law of conservation of mass. You might not have part of the materials for this, but maybe you have a neighbor who does. If you have a neighbor who has a kitchen scale, you need one of those, okay? If you have access to a kitchen scale, if you don't, I'll give you an idea how to make something that would work, but hopefully you've got access. Steal a ketchup container from Wendy's, okay? Recycle one if you need to. Take a ketchup container, put vinegar in it. Take a teaspoon of baking soda. Get a Ziploc bag, a small sandwich bag. Put the ketchup container of vinegar in one corner. Put the teaspoon of baking soda in the other corner. Seal up your Ziploc bag. Put it on the balance. Get the mass. Everybody with me? Then dump the vinegar. Keep the bag closed. Don't open the bag. Keep it all closed, but just shake it up. Now what's going to happen? It's going to fizz, it's going to have a chemical reaction. I heard somebody else say something. Somebody said bubbles, but I thought I heard something else. Tell me what I'm going to see besides, I can see air. I can see a gas created, whoever's telling me that. What's the bag going to look like? Is it going to expand? Is it going to blow up? Okay, okay. So I'm having, and you've already said this, I'm having a chemical reaction taking place inside the bag, right? This is a closed container. So once I have the reaction take place, put it back in, or on rather, the balance. What should the mass be? It should be the same. And that proves the law of conservation of mass. Now, I have another experiment for you that I'm going to do. Actually, I'm not going to do it. My daughter's going to do it. We have a question that a student asked me, and it really started making me wonder. Boiled eggs, first of all. Boiled eggs, are boiled eggs a chemical reaction or a physical reaction? Boiling of eggs. Pretend I got here early and I had a boiled egg and you were not in the room and I cracked and peeled my egg and then you walked in the room. Would you know I had a boiled egg? Why? The smell. Now, reverse the story. Go back. I got here early. You weren't in the room. I had a raw egg. I cracked it. You walked in the room. Can you tell I had a cracked egg? No, you can't. That raw cracked egg you could not smell. Now you answer the question. Is boiling an egg a chemical reaction or a physical reaction? It's a chemical reaction. That is a chemical reaction because a gas is formed. Put your phones up, all the way up. That's the second phone I've seen out. Put them up. All the way. All right. So, it's a chemical reaction. Now, here's my question for you. Is everything needed for that chemical reaction inside of the egg? All right. How do we know the answer to that? How would be a test? What's a test we could do? Say it again. Well, possibly, but what is proof that the law of conservation of mass is true? If the mass is the same before and after. So the experiment that we're going to do is does boiling an egg obey the law of conservation of mass? So we're going to boil eggs. We're going to test their mass ahead of time, test their mass afterwards, and see if their mass is the same. Now, do you think a boiled egg has a greater mass than a raw egg? Some of you think it does. It feels different. That's what people will tell me. It feels different. It feels heavier. It feels more dense. That's what people tell me. If that's true then, and it does have a greater mass, then what is that meaning? That means that not everything in that egg is in the egg to begin with, is it? That means there has to be something going into that egg. Does that make sense? You follow what's going on? So this is our science fair project because we don't know the answer. So do it though. You do your own experiment and tell me what you find out because I don't know. I think it obeys the law of conservation of mass. I think that a boiled egg and a raw egg are going to weigh the same. But people think they don't. So I don't know. We need to test it. So anyway, there's an experiment for you to try. We will not be writing a chemical equation for our boiled egg, but you will be on other things. So let's look at how to balance these. First, we need to know what the symbols mean. The arrow is the reaction arrow. The triangle means heat. S solid, L liquid, G gas, and AQ aqueous solution. So what is C2H6O? Tell me about it in this equation. What is C2H6O? It's a liquid, and is it a reactant? Good. Why is O2 written O2? It's diatomic. And what is it in this reaction? What is oxygen in this reaction? It's a gas, and it is a reactant. What are the products? Carbon dioxide and water. Okay? How do we balance it? So let me tell you my way of balancing. My way is not writing everything down. If that's how you learn to balance from high school, I will not be writing everything down. I look at it, and I literally just go back and forth. Okay? So I say, how many carbons? 2. Go over to the right, how many carbons? So using a pencil, what should I put here? 2. So 2 C's, yes? Then I look at my H's, and I see how many? And over here I have, so what am I going to put in front? And that makes 6. And I have 1 O. Here I have 2. That makes a total of 3. Here I have how many? 4 plus these 3 is, 4 plus 3 is 7. Now then, I have 1 here. I have 2 here. I don't want to mess with this. Why don't I want to mess with this? If I mess with this, it's going to change everything else. So I'm just going to deal with oxygen because that's what matters. What do I need to put here? Added to 1 will make 7. So if I put a 3 here, then that makes 6 plus 1 is 7. So I double check again. 2 carbons, 6 H's, 6H. 1 plus 6 is 7. 4 plus 3 is 7. So this is balanced. Before we do any more, I'm going to give you my hints. So let me just go down here to the bottom and give you the hints. And then we'll do these. Here are my 2 hints. If have the same polyatomic ion on both sides, keep it together. If you have the same polyatomic ion on both sides, keep it together. That's one real good reason to know your polyatomic ions. And then the other hint, if an unusually hard atom to balance, do everything else first. If an unusually hard atom to balance, do everything else first. And we will see examples of both of these in my examples. So let's go back to the top. Do we have the same polyatomic ion on both sides? Yes or no? First one, do we have the same polyatomic ion on both sides? Yes, you do. You have nitrate on each side. What else do you have? Chromate. You have nitrate and you have chromate. So leave it as nitrate. That's my point. Don't break it down into nitrogen and oxygen. Leave it as nitrate. So what we're going to do is we're going to look at this and we're going to say 1 ppb on the left, 1 ppb on the right. How many nitrates on the left? How many nitrates on the right? 1. So what are we going to put in front? 2. How many K's on the left? 2. How many K's on the right? 2. How many chromates on the left? How many chromates on the right? 1. Now double check it. 1 ppb, 1 ppb. 2 NO3s, 2 NO3s. 2K, 2K, CrO4, CrO4. That is so much simpler than taking it 2 N's, 6 O's, plus those 4 O's. It gets really complicated. Leave it together. All right, go to the next one. Wake up, Gus. Go to your next one. Tell me what to do here. 1 M in, and you have to really pay attention where your arrow is on this one because you want to put it over here. 1 M in, 1 M in. 2 O's. What about here? So what I'll put in front? 1 H, and over here I have 4. I have 4. So what do you think I need to put here? And that made 4 Cl's. How many do I have on the right? 2 plus these 2. Now again, it would help probably if you kind of really make a note of where the arrow is. So 1 M in, 1 M in, 2 O's, 2 O's, 4 H's, 4 H's, 4 Cl's, and 2 plus 2. Yes or no? All right, the next example, look at it. Tell me what you come up with. Guys, try it. Some of you are sitting there. What do you come up with? It's balanced. It's balanced, but some of you are snoozing. So 2Na, 2Na, 1C, 1C. 3O plus 2 is 5. 2 plus 3 is 5. 1S plus 1S is 2. There's 2. So this one is balanced. That means don't put any coefficients. It's balanced. All right, let's look at the next one. What'd you come up with on it? Try it. Your test will have this as multiple choice. And the question might say something like this, so I'm going to let you answer it this way. What are the coefficients of the following reaction? And then you just say the digits. And if one of them is 1, you still say 1, but we don't write 1. So what are the coefficients for the following reaction? I heard 1, 1, 2, 1. That's correct. So 2 silver, 1S, 1S, 2 H's, 2 H's. The next one does not have exactly the same polyatomic ion on each side, but there's something you can keep the same. What is the same? Good. Do you see how really this is bicarbonate? And on this side it's just carbonate, but they both have carbonate in them. So you can just read it as CO3 and then balance the CO3 separately. So try that and see what you get. So I see 1 mg, 1 mg, 2 H's plus 1 H is 3. Over here it's only 2. Now, this is where I'm going to make a strong suggestion. Yes, you could go ahead and put something here and then do that and worry with the H's. But immediately, if you are thinking, you probably are realizing, you know what, those H's look like a little bit of trouble. Skip it. Don't spend 5 minutes on it. Don't spend a minute. Skip them right now. Chances are they'll work themselves out. So skip the H's. Now, how many CO3s do we have? On this side, how many do we have? Just 1. So if we put a 2 there, that made 2 CO3s. Then let's look at these Cl's. Remember, we're skipping H. How many Cl's? How many Cl's? So if we put a 2 back here, now let's go back through it again. 1 mg, 1 mg. How many H's now? 4. Are you seeing 4? 2 plus these 2. Now how many do we have on this side? Didn't that work itself out? And then 2 CO3s, 2 CO3s, 2 Cl's, 2 Cl's.
So the 2 only outside the parentheses only applies to the bicarbonate.
The 2 outside the parentheses applies to what is inside the parentheses. Correct. Correct. Up here, same thing. 2 N's and 6 O's. But again, we didn't break that down. But we called it 2 NO3s. All right, the last one. Do it. What do you get? Any questions on these? Now then, I wanted to make a comment. These are obviously really easy. All right? These are not hard ones. I've used these to show you some of the tricks, but these are not hard ones. I'll tell you that right now. These are easy ones. You need to start on your sapling homework. Take some time to pull down that online homework, or online book rather, and go to the chapter that deals with equations and find some examples. The answers are already there. Practice some of these because you need some more practice, okay? Strongly encourage you to practice these. I'll be honest with you, I don't think that I have a practice worksheet for this on Blackboard. I know I have a practice mole worksheet, which we're going to get to now, but I don't think there's one for equations, so you'll need to do some of those on your own. All right, mole. If you had high school chemistry, some of you may have had a teacher that really got into mole day. Yep, some of you did. So can you tell me when mole day is? Anybody know? It's October.
Is it third? No.
You're close. You got a 3 right. 23rd, October 23rd. It's October 23rd. So we're in the mole month, but we're not to mole day yet. Now, some of you, when I say mole, you're thinking, or actually I'm thinking today when I'm walking across the yard and I'm seeing these piles of dirt that the moles have dug up in my yard. That's what I'm thinking. But that's not the mole we're talking about right here. That's what you were thinking. The other thing I think about was actually all my life up until when I was in college, I had a mole on my neck right here, and I had that taken off. But that's not what I'm talking about here either. We don't have a day for moles on your neck. But that's not what we're talking about. So if you know what a mole is, not the mole or the mole, if you know, or that person that, there's one more mole. What's the other mole? The person that's kind of like the snitch on the company, and they're telling all the stuff and secretly. We're not talking about that mole either. Okay. Yes, yes, yeah. So we're not talking about any of those moles, but some of you know the mole we're talking about. Now, if you know the mole, if you know the mole we're talking about, can you give me an example, not using mole, of another scenario that's like a mole? Now, it's hard for me to ask the question the way I'm trying to get it asked. Let me say this. If you truly know what a mole is, chemistry-wise, then you're hopefully thinking in your head, mole means da-da-da-da-da-da. Which means then that the word mole is a word that means a. So give me another example of that. Pi. That is this group of students. You all in my 8 o'clock class are the only students who have ever told me pi before. Nobody has ever said pi before. I've never even thought about pi. It's similar. It's not exactly the same, but it's similar. Pi is a word, sort of. That means what? When I say pi, you know it means what? 3.14. In other words, it's a word that means a number. Mole, the way we're talking about it, is a word that means a number. Now, what number does it mean, those of you that know it? It's times 10 to the 23rd, 6.022 or 6.02. Very good. So it's either 6.02 or 6.022, depending on what teacher and what book they had, times 10 to the 23rd means 1 mole. That's exactly right. Now, before we keep going on moles, though, because I really want you to understand what the concept is, what are some other words that mean numbers? Has everybody signed in? What are some other words that mean numbers? No, I'm saying a word that means a number. You're doing chemistry.
Like when you say like a cup of something.
Yes, but not a cup.
Like pint. Well, I don't know. Like ounces.
Dozen. What does dozen mean? 12. Half a dozen is 6. Baker's dozen's 13. Let's get off dozen now. Century is 100. That's the one people don't usually say. Few is too relative. Couple. Let's go couple. Couple means how many? Pair means 2. Now I'll give you some more complicated ones. Let's go to paper for a minute. What's a ream of paper? Anybody know? 500. A ream is 500. What's a gross? Anybody know what a gross is? 144. Don't ask me where they got that. But a gross of pencils would be what? 144 pencils. A pair of pencils would be 2 pencils. Now, don't ask me about a pair of pants and a pair of glasses and all that. Don't ask me about that stuff. We're not going to go there. But a couple eggs would be 2 eggs. A couple of people would be 2 people. A mole of eggs would be 6.02 times 10 to the 23rd eggs. A dozen eggs would be 12 eggs. A mole of pencils would be Avogadro's number, since you were using that phrase earlier, which is the same thing as 6.02 times 10 to the 23rd pencils. A dozen pencils would be 12 pencils. What I'm trying to get you to see is, did my unit change depending upon what I was talking about? If I'm talking about eggs, the unit is eggs. If I'm talking about pencils, the unit is pencils. But the number, the quantity is the same no matter what I'm talking about. If I'm talking about eggs, the unit changes, but if it's a dozen, it's still 12, no matter whether it's eggs or chairs or water bottles or pens or donuts or whatever. So what we're going to be dealing with is Avogadro's number, which is the name, the fancy name for 6.02 times 10 to the 23rd, and I'm putting this generic particles because the particles change depending upon what I'm dealing with. You need to know what the choices are. So here are our choices. 1 mole of any element is 6.02 times 10 to the 23rd. Now you tell me, what is the smallest particle of an element? Say it. Atom. So 6.02 times 10 to the 23rd atoms. 1 mole of any molecular compound is 6.02 times 10 to the 23rd. Now, what's the smallest particle of a molecular compound called? I'm hearing it. Molecules. Molecules. Now, this one's a little harder. 1 mole of any ionic compound is 6.02 times 10 to the 23rd. And what you want to say are ions. But they're not ions. And let me explain to you first why they're not ions, then I'll tell you what they are. Let's say that this is an ionic compound. If it's a little group of staples. If this is an ionic compound, then the whole thing together, if I only have one particle of an ionic compound, this is called a formula unit. That is a formula unit because it's still together as an ionic compound. What these are when they're separate are called what? You know this. Ions. You wanted to say that ionic compounds are made up of the smallest particle called ions, right? But when they're ions, are they together? No, that's what I'm trying to show you. A formula unit is when it's together. That's the smallest particle. When they're separate, they're ions, but I'm talking about what's the smallest particle when it is together, and that's called a formula unit. So, what do you think a number and its unit equaling another number and its unit is going to be used for? Conversions. Very good. So, before we start doing conversions, let's talk about the things that we all want to do, and that's shortcut. The shortcut is nobody wants to write units. So what's the abbreviation that we can use? Mole cannot be abbreviated any lower than MOL. So it always has to be MOL. 1 mole, MOL. You can't go any lower than MOL. Atoms, you can't really go lower than atom. You don't need to go any lower than that, so keep it atom. Molecule, what do you think? Can't be MOLE, so what's it going to have to be? There you go. MOLEC is the shortest you can go, and I'm not trying to be crude, but I will use FU on formula unit. Okay? So these are the abbreviations that we will use, and the next statement tells you when you are going to need them. It specifically tells you when you are converting to or from atoms, molecules, or formula units. I'm sorry, I left off moles. When you're converting to or from moles to atoms, molecules, or formula units, you're going to use Avogadro's number. What is Avogadro's number? Okay, now before we go any further, I got a couple questions to ask you. This is not trying to trick you, okay? I'm not saying which is heavier, a pound of feathers, a pound of lead, a pound's a pound. We all know that joke. I'm not tricking you, okay? Just answer the questions. If I have 1 mole of copper, what do I have? .02 times 10 to the 23rd atoms. Yes or no? Okay. So if I have 1 mole of copper, I have 6.02 times 10 to the 23rd atoms of copper. If I have 1 mole of water, let's say I have 1 mole of water, what do I have? 6.02 times 10 to the 23rd molecules of water. Now, why did I say molecules? What kind of compound is this? Molecular compound. What if I say to you I have 1 mole of sodium chloride? What are you going to say I have? 6.02 times 10 to the 23rd formula units. Why is it sodium chloride formula units? There you go. So you follow what I'm doing. And every one of those could be conversion factors if I ask you, for instance, how many formula units are in 32.78 moles of sodium chloride, which is what we're going to do on the next page. Okay? But all of our questions do not deal with Avogadro's number and moles. Some of them deal with mass. And this is where the label that your periodic table has for mass comes into play. Some of you noticed on your periodic table in the legend that it said something about grams per mole. Does anybody remember that? Seeing that on your periodic table? Well, now that is the unit we're going to use for molar mass. The molar mass is in grams per mole. Up until this point, we had said it's the generic unit, AMU, standing for atomic mass unit. Now I'm telling you, since we know about moles, the mass that's on the periodic table is for 1 mole of that substance. So if I tell you I have 1 mole of carbon, I can say one thing I know if I have a mole of carbon is I have what? For sure. What have I already talked about tonight? 6.02 times 10 to the 23rd atoms of carbon. But now I could also say if you have a mole of carbon, what do you have? 12.01 grams. Because this mass of every element that's on the periodic table is actually the number of moles, grams rather, per 1 mole of that element. It's the number of grams per 1 mole. So I'm going to go through this. Grab your periodic table. You're going to need it anyway. Excuse me? Absolutely. Anyone else need a periodic table? Just pass them back. They're coming back. Just pass them back, guys. Okay, so tell me, looking at the periodic table, tell me, what is the mass of 1 mole of titanium? Remember how I round it. Go ahead. 47.88 grams. What is the mass of 1 mole of sulfur? 32.07 grams. Good. What's the mass of 1 mole of chromium? 52.00 grams. That's how I would expect you to write it, okay? Please round to the nearest hundredth for my class. Sapling, round it to the nearest hundredth. It's not going to hurt you to do it there on sapling either, okay? Now then, let's use this information, and it tells us when converting to or from mass to moles, use the periodic table mass, which is now in units of grams per mole. And remember, round to the 2 places after the decimal. But not everything is on the periodic table. Water, for instance, isn't on the periodic table. So what do we have to do? You add them up. You get the sum of the masses. And so it tells you that to find the molar mass, which is the same thing as molecular weight, which is the same thing as formula mass, you add the atomic masses of all the atoms in a compound. And so where does this 2 come from? 2 H's times the mass of hydrogen, add that to 1 oxygen times its mass, and what's the mass of water? Which means, looking at my picture down here, and then we'll come back and do this one. This picture shows us 1 mole of water molecules. This is it. This is what 1 mole of water molecules looks like. And we just did it as 18.02 grams. So that means if I say to you, I want you to go to the lab and I want you to bring me back a mole of water, what are you going to bring me? Very good. Now, I'm going to give you some that aren't on here. I want a mole of carbon brought back. What are you going to bring me? 12.01 grams. I want a mole of potassium. What are you going to bring me? 39.10 grams. Guys, some of you are looking around. Where are they getting these numbers? Because what is that mass on the periodic table? The mass in grams per 1 mole. So if I say to you, bring me a mole of such and such, you shouldn't be flipping out. There's no reason. It's right on the periodic table. That's a mole. What if I said to you, bring me 6.02 times 10 to the 23rd atoms of copper? Don't flip. Don't count. What are you going to go do? Look at the periodic table and find copper. And know that that's 1 mole, and 6.02 times 10 to the 23rd is 1 mole. And you're going to bring me what? Is it 63.55 grams? Does that make sense? All right. This picture then shows us 18.02 grams of water, which is 1 mole of water. What else could I write up here that this picture shows me? Well, forget the other things. I'm talking water. I've said it, we just didn't write it. What else does this show me? It shows me 1 mole of water molecules, it shows me 18.02 grams of water molecules, and it shows me 6.02 times 10 to the 23rd molecules. This shows me sodium chloride. Now, the way I would have calculated this, it would be 58.44. So what is this picture of? It's 1 mole of NaCl, which means what is here? Formula units, or 58.44 grams. Does everybody agree that all three of those are the same? And then the last one, this is white table sugar. This is sucrose. This is sweet. This is what we like. This is 1 mole of sugar. C12H22O11, I would have added this up as, I think it's 342.34 if I remember correctly. If I did it in my, 342.34 grams. So if I said to you, I want you to go to the lab, bring me back a mole of table sugar, what are you going to bring me? 342.34 grams. Do you realize it's almost a pound? Not, it's close to a pound. It's about 2/3 of a pound. Does that make sense? Okay. So you're going to bring that back, and then what can you say you've brought me? 6.02 times 10 to the what? 23rd molecules. Good job. Okay. All right. Find the molar mass of barium phosphate. Find the molar mass, just right there somewhere on the paper. You can do your calculator only, or you can actually do the numbers. Do I have anybody here from the 8 o'clock class? Okay. So find the molar mass of barium phosphate. Somewhere, either on your calculator or on the paper, you should have this. Yep, sorry. And your answer should be what? Do you get 601.93? Yes or no? Do you see what we've done? All right, then flip the page and let's start calculating. if you paid attention to the previous page, this should not be a hard page to do, because it tells you right underneath our mole scenario when to use what. So when I look at this question and it says how many grams are in moles, the question deals with grams and moles, which tells me where am I going to go to get information. Second problem. Periodic table again. Third problem. Do I use the periodic table in the third problem? Nope. Instead, I'm going to be using what? Avogadro's number, 6.02 times 10 to the 23rd. By the way, somebody is wanting to know why they call that Avogadro's number. Amedeo Avogadro is a scientist, chemist, who we honor by calling that his number. He did not come up with the number, but we honor him by calling it his number. Okay? So the fourth problem, rather, molecules and moles. What are we going to use there? It doesn't say anything about mass, so what are we going to use? The big number? Avogadro's number? The Italian guy? I don't even think he was Italian. I can't remember now. All right, so let's get started. 3.50 moles. What do you find on your periodic table to help you out? What's the mass of lithium? 6.94 what? Where is that going to go? So 6.94 grams in what? 1 mole. What cancels? Moles. What are we left with? Does this look familiar? Now, why did I drill dimensional analysis in your heads? Because now this shouldn't be hard. This should be like, oh, I know how to do this. Does that make sense? So what's your answer? 24.3 grams? Is that what you get? Yes or no? All right, do the next one. You round to proper significant figures. Can't forget what we've learned. 333, significant figures. Now, on this one, is aspirin on the periodic table? So what do you have to do? You have to find it. So you have to go find and calculate aspirin's mass. What do you get for this one? Give it to me in scientific notation. 1.39 needs 3 significant digits. 1.39 times 10 to the negative 3. What's my unit? Could you also have 0.00139 moles? Yes. Now, are we getting this? Some of you knew this coming into this classroom because you had this drilled into you. So you understand what you're doing now. For those of you that didn't know how to do it, is it making sense? So go to the next problem. Do we use the periodic table for the next problem? No. So what's our given? How many moles are in this number of atoms? In order to solve this, what do you have to use? The number of atoms in a mole of anything, which is what? So where 6.02 times 10 to the 23rd atoms go? 6.02 times 10 to the 23rd atoms goes on bottom. What goes on top? 1 mole. Atoms cancel. Now, I've seen that students don't remember how to plug this in your calculator. So, EE. You don't have to give me the answer in scientific notation, but you do have to give me proper significant figures. And Avogadro's number counts. So how many significant figures? So what's my answer? 1.14 times 10 to the 4th moles, or 11,400 moles. Now, if you did not get that, then let's talk about how to put it in your calculator. We ready? 6.87, hit the EE key, 27. Divided by 6.02, hit the EE key, 23, equals. Now do you get it? Yes or no? Okay. All right, you do the next one. You do this next one. What do you get? 1 point. $24. Run your numbers again if you're not getting that. Run your numbers again. Did everybody get that on your calculator? All right, I have tried to make this fairly simple in the sense that these two problems were basically the opposite of each other. These two problems have been the opposite of each other. Here you just needed the periodic table. Here you just needed Avogadro's number. But now we go to combined, meaning you're going to need Avogadro's number and the periodic table. And there's something else in here that's a little tricky. It says what mass in grams of oxygen is in 2.85 times 10 to the 24th molecules. So as soon as you see mass, you think periodic table. As soon as you see the word molecules, you think 6.02 times 10 to the 23rd. So it means I have to use both. But then I'm hoping your brain says to you, oxygen is an element. Why didn't she call these atoms? Because I said molecules, because I'm talking about what? Diatomic oxygen, which means this is O2. Is that going to make a difference in my mass? Yes. So try it. I want you to try this on your own right now. You try it and then I'll do it. You try it. We are going to have time for some of you. I'm not going to have all of you probably stay to look at your test, but we will have a time to look at your test and should actually get out early. So be with me for the next few minutes and then we'll be able to get done early tonight. What comes next? Tell me what comes on top. 1 mole on top. What goes on bottom? And then what's next? 32 grams in 1 mole. Why? Because it's diatomic. And then your final answer is what? I have 151 grams. Yes or no? All right, so we did two the same little problems, one that combined, and then I go, okay, you know what you're doing now, let's whammo. And that's what this next one is. Because here's my opinion. I have drilled dimensional analysis into you. Everything you learned about dimensional analysis is still true now. This next problem takes all of that and adds to what we've been doing now. So here's my question. Right now, I want to know how many molecules of water I drink if I drink 3 quarts of water. In order to answer that question, you have to know how many moles I drink, right? And to get moles, you had to, other than molecules, you'd have to know what? Grams. So now 3 quarts equals how many grams? That's a back at the beginning of the semester question. There isn't a conversion to get you quarts to grams. I can tell you that one. Don't be thinking if there is one. There's not. But what is it? You remember my bell? When did I ding my bell? Say it. Density. Why does density matter here? Because quarts is what kind of unit? Volume. I'm trying to get volume to mass. In order to do that, what do you have to have? Density. What's the density of water? 1 gram per milliliter. Try it. Try this problem. You should be able to do this problem. Try it. I'll tell you the conversion from quarts to milliliters, or milliliters to quarts. Do you know what it is? 946 milliliters in a quart. You need that. Try it. 946 milliliters in a quart. What do you start with? 3 quarts? What comes on top next? In 1 quart. Then what? This is where density comes into play. 1 gram per 1 milliliter. That's where we get into mass. That's from beginning of the semester. Now, finish it from there. If you got stuck there, finish it from there. Try it, guys. Some of you just wait for me to do it. And then you wonder why you never understand anything. You got to try. You got to spend a little time. What comes next? 1 mole over 18.02 grams. Then what's last? 6.02 times 10 to the 23rd molecules per 1 mole, because the question asks for molecules. Good. When I run my numbers, what do I get for my final answer? 9.5 molecules. Yes or no? Try this one. What do you have to know in order to do this last one? The mass. In order to know the mass, you have to know the formula. What's the formula? NH4NO3. Good job. NH4NO3. I want you to get it set up. I want you to start it, and then we're going to actually put everything up, and I think I am going to move you around a little bit, and we're all going to look at our test and get it over with tonight. Tell me your layout. You don't have to tell me the whole thing. Tell me your layout. You're going to go pounds to grams, which is just 454 grams in a pound. Then you're going to go grams to moles using the mass that you calculate. And then you're going to go moles to formula units, which is similar to molecules, using Avogadro's number. Okay. All right. I will do this one the first thing on Wednesday. So you've got this in your mode of thinking now, hopefully. Couple things I want to point out while you're putting your stuff up. On Blackboard, under practice homework or extra practice worksheets or something like that, there is more practice over moles. You need to do more practice than just what's on these notes. You need to do more. The practice that are on Blackboard are my problems with answer keys. So I would strongly encourage you to look at that, okay? Take some time to look at those.